Hello everyone, and welcome to today's chem lesson. Today we are going to begin our discussion about ionic bonding, which occurs when electrons are transferred from one atom to another. Now this bond forms when a metal and a nonmetal come together, almost exclusively when a metal and a nonmetal come together, because of the large difference in electronegativities of these types of elements. Metals are almost exclusively very low electronegativities, and nonmetals are almost exclusively very high electronegativities. And that combination of one very weak pull and one very strong pull almost always occurs or results in the transfer of electrons, the nonmetal taking the electron away from the metal. When we think back and look at something like francium and fluorine, two of our corner elements that we used when we looked at our periodic trends, right? Francium in the bottom left, fluorine in the upper right. We talked about how francium has 1 electron, fluorine has 7. When these two elements get together, the very strong electronegativity of fluorine, combined with the very weak electronegativity of francium, results in francium losing an electron and this entire outer shell, and fluorine gaining that electron, making francium now have an empty shell, and fluorine now having a full shell. Since francium lost an electron, it gets a positive charge, making it a positive ion. Since fluorine gained an electron, it gets this negative charge, making it a negative ion. And now we see the actual bond, which is the fact that we have a positive thing and a negative thing that are attracted to each other, because as we know, opposites attract. Positives and negatives are going to stick together. And so two things that were neutral become charged and then stick together because of these opposite charges that they now have. And before we really dive in to look at this in more detail and take a look at some of the drawings and some of the naming conventions that we're going to have to look at, we need to address the properties concern. When we talk about ionic substances, something like table salt, the properties of salt are very different from the properties of the individual pieces that make up the salt. Sodium is an explosive metal. Chlorine is a poisonous gas. But together they make something that you stick on food to make it flavorful. The salt has lost the explosive properties of sodium. It has lost the poisonous properties of chlorine to become something totally different. And the same can be said of any other ionic compound. The properties of the compound are not the same as the properties of the individual pieces. And so francium fluoride has a different set of properties than francium and fluorine apart from each other. Sodium chloride has a different set of properties than sodium and chlorine apart from each other. When we look at ionic compounds as a whole, and we take a list of all these different compounds, we can say that they share a similar set of properties. Almost all ionic compounds are hard, good conductors of heat and electricity as long as they are melted or mixed with water, and have high melting points and high boiling points. these three sets of properties are universal across ionic compounds. And it makes it easy to identify an ionic compound if you have one. Right? Being able to check these physical properties is a lot easier than having to look into the chemical formula with more in-depth equipment. And so knowing that you have found this mystery substance that has a high melting point, a high boiling point, and conducts electricity really well in its aqueous form is a pretty good indication that this thing is an ionic compound. Which ionic compound is a different question that can be answered with a different set of experiments. Another small little tangent to go on is the idea that along with new compounds and talking about these ionic bonds and ionic substances comes a little bit of vocab. And those two new vocab words we're going to look at are anion and cation. And as you might be able to tell from the endings of these words, these are two alternate words to use for ions. An anion is a negative ion. A cation is a positive ion. So it doesn't actually represent anything new, it's just a new word for an old concept. If you don't like the cat and paw mnemonic device, you could always remember that the T in cation is like a little positive sign, telling you that cations are positive. But if we take this back and look at our francium and fluorine again, with our missing outer shell here, our full outer shell here, which one of these was the cation and which one of these was the anion? Do you remember what these charges are? Which one is positive and which one is negative? So here we know that francium has lost an electron, making it positive, making it the cation. And fluorine is negative, having gained an electron, making it the anion. Right? Well done, Joaquin. So again, these aren't new concepts, they're just new words for old concepts. And you might hear talk of the cation in this compound or the anion in this compound. And it's important to be able to make that connection between the vocab word and the specific charge of the ion you are talking about. But the last time we looked at drawing shell models and focusing in on valence electrons, we didn't draw these out, right? We didn't use this semicircle drawing method. We did something else. The last time we were looking at something like this, we were doing Lewis dot diagrams. And so let's see how Lewis dot diagrams change if we are looking at an ion. When we do a Lewis dot diagram, just a reminder, we put our symbol in the middle and we put dots around the symbol in order to represent the number of valence electrons. Something with 3 valence electrons would get 3 dots in the first, second, and third spots. A 4th, 5th, 6th, 7th, and 8th dot go around in this order. And we started using this because it was easier to keep track of than having to draw all the shells, which we don't really care about how many electrons are in them. And so we get rid of the extra information. We keep the number of valence electrons and the identity of the element. So let's think about francium and fluorine. All right, let's look at FRF and do a before and an after. So we've got francium and fluorine. Francium has 1 valence electron. Fluorine we know has 7 valence electrons. So we correctly put our dots around our symbols to make our Lewis dot diagrams for the before. In order for these things to bond, though, there needs to be a transfer of electrons. Fluorine is going to take the electron from francium. And we are going to end up now with fluorine with all 8 valence electrons filled. And francium is going to have no valence electrons left. But if we're being honest with each other, if we're looking at this, this doesn't look like something that has formed a bond. This just looks like 2 elements that I drew. In order to make francium fluoride, this after, into something that has bonded, we need to put 2 new pieces. We need to put brackets around each ion, and also include the charge outside of those brackets. And putting them like this close together is going to show us that they have been bonded together. Marking them as ions is important, but not as important as putting them next to each other like this. Right, it's slight, but there's a gap here that isn't present on the other side. What about something like calcium oxide? Can you make the before and after correctly for calcium oxide? I'm going to give you about 1.5 minutes here to try to put that together. Let's take a look at these two elements here. Calcium has 2 valence electrons, which both are going to go on top, following our diagram from before, right? Following our template. On the other hand, oxygen has 6 valence electrons, which are going to fill in along the sides like so. These are our before pictures. Now for our after, we should see calcium losing both of its electrons, being taken by oxygen. And our new electron configuration, our new Lewis dot diagrams, should look like this. But before we are completely finished with them, we need to remember to put our brackets around the calcium and the oxygen, include the charges, a +2 for calcium because it lost 2 electrons, a -2 for oxygen because it gained 2 electrons, and we should see this as our final drawing. Remember, when we're trying to decide what gains and what loses, calcium has the option of losing 2 or gaining 6. It will always pick the lower number. Same thing goes for oxygen. Losing 6 or gaining 2, it will always pick the option with the smaller number. Next time, we're going to jump into how we get the names for these substances. All right, we know sodium and chlorine make sodium chloride. And we're going to talk about the naming conventions and the rules that come alongside with making an ionic compound. But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.